Alright, so welcome back to Particle Physics and the Standard Model. This is lecture 22. So in the last lecture, having constructed the Hamiltonian for a spin 0 field, we saw that an immediate consequence was that you had a 0 point energy that for whatever cutoff that you chose, any sensible cutoff that you choose, you get a 0 point energy that is many orders of magnitude larger than what is actually measured as the dark energy or the vacuum energy or the cosmological constant, right? And then there was no way to get away from this, because even though you have some other free parameters, you have to fine tune these free parameters up to hundreds of decimal places in order to cancel them against what you are calculating as a 0 point energy to get the measured value, right? So it's an extreme fine tuning problem. Okay, we can move on from that concept and go back to some other technical aspects of describing all these things in terms of quantum fields. Okay, so I promised you when I was motivating quantum field theory that the existence of antiparticles is only explained in the quantum field theory description, right? So we'll see how that comes about. Okay, it simply has to do with how you write down the general solution for these fields. Alright, so what was the general solution that we had for the real scalar field? Remember, we enforced the condition that the field that we are working with is real, right? When we did that, this was our solution, correct? And the general solution had an operator A, which we associated with a destruction operator, destruction of particles, and an A star, which we associated with creation of particles with momentum k, and then each had its own energy dependence. The A got married to a term with positive energies, and the A star got married to a term with negative energies, correct? Although it's not really a negative energy, we did rewrite all this in terms of these propagating degrees of freedom. It's a negative energy only if you interpret this as a wave function, correct? The energies are positive only, actually. Alright, the actual state that you are thinking of is still positive. It's just that the mode expansion looks like this, correct? Now that can now be generalized to complex scalars, where, in other words, phi star of x is not equal to phi of x. Okay, so do you remember that when we started out, the general solution we wrote down actually looked like this. So I'm doing some simplifications already. I'm not going to go back to the very first step, but nevertheless, remember we started with two different operators, A and B, correct? And only when we imposed phi equals phi star, we got this condition, correct? B star of minus k. Remember this? You can go back to those 2 or 3 lectures back and you'll see that this is how we were deriving the general solution in the final compact form, correct? But now we are not going to impose this, so I'll just erase this so that we don't have any confusion. We have just this as the general solution, alright? Except I'm going to do one little change. Earlier we just had a B, but now I'm going to basically change variables. I'm just going to call B as B dagger, that's it. So that B dagger becomes B. Okay. So I'm just going to put a dagger here. All right. So I'm just going to call this the general solution. Why? Because that gives a better physical meaning for what all this is. Okay. We said now that this was a creation operator, sorry, this is an annihilation operator and this is a creation operator. Correct? When you have a dagger, it becomes a creation operator, right? I can write down a set of commutation relations for A and a set of commutation relations for B dagger. Correct? Just like from over here, these commutation relations. Agreed? So in this notation, it becomes clear what these operators are doing. Since the B dagger is associated with the term that presumably carries the negative energy, it's not a negative energy, but it looks like we started out with a term that looked like a negative energy, correct? The interpretation is that this term in the mode expansion corresponds to destruction of particles and this term corresponds to creation of antiparticles. Do you agree with this? See, without any effort, by just writing down the general solution in terms of plane waves, you can see immediately this accommodates the description of antiparticles. Correct? So you cannot write one without the other. They come together, they always come together in the general solution and you have to write down the general solution. Correct? Similarly, if I were to write phi dagger of x, that's just nothing but an A dagger of k, but now I have an e power minus ikx plus a b of k e power plus ikx, and again what do these terms correspond to? The A dagger term corresponds to creation of particles and the B corresponds to destruction or annihilation of antiparticles. Okay, this is how you should interpret a quantum field. Okay, there's a tendency to think of this as some particle and this as an antiparticle. Absolutely not. The field already contains, when you have a complex field, the field or the operator already contains in its mode expansion the operators for both particles and antiparticles. It's just that they don't come as just creation in both sides. They accommodate destruction of particles in one and creation of antiparticles and vice versa. Okay? Okay. One little comment I want to say here is that now since you have two different degrees of freedom, they are in a sense distinct degrees of freedom, although they come together, you can embed both of them in the same field. Because of that, what would happen in the Hamiltonian is that at the end of the day, you will end up with a term that goes as 2 times the 0 point energy. Okay, of course you can redefine this as the 0 point energy, but there is an E naught coming from the particle states and there is another E naught coming from the antiparticle states. Okay, so these two 0 point energies add up, and of course the bare term is always there, it's just there in the Lagrangian. That will become your Hamiltonian, but otherwise there is no other change. Otherwise the cosmological constant problem and everything else remain the same. Okay, just a factor of 2. Okay, very good. So I think that ends our discussion of toy quantum field theory, which already seems to give you a lot of these problems, and it will give rise to other problems as well, and we will see how to counter each of them as we go along. Okay, so even for spin 0, even for the simplest degrees of freedom, you have all this rich structure accommodating destruction of particles, creation of particles, the existence of antiparticles, the existence of indistinguishable particles. All of this you can already see, right? Most of the things that I promised when we started motivating quantum field theory, right? Okay, then that will allow us to go on to how to deal with spin 1 states in quantum field theory. Okay, so what are some spin 1 states? The photon, Z boson, W bosons, what else? Of course there's a gluon, right? The rho meson, omega meson, etc., etc., right? How do we describe all this? How do we embed these particles into quantum fields the way we did it for scalar fields? Okay, let's begin our discussion with something that we expect from all quantum field theories, because it becomes important especially in the context of spin 1. Okay, the expectation is that you want the energy density coming from the stress energy tensor to be positive definite. You want that to be bounded from below, right? Otherwise you're just going to go to minus infinity. All the energy configurations will go to minus infinity, right? And all hell breaks loose, right? So that means we can begin with the energy momentum tensor. I'm not going to derive this. This again should be there in any field theory book. Even otherwise it should look pretty intuitive, right? So I write okay, oops, dou nu of phi n minus g mu nu times the Lagrangian. This is the energy momentum tensor agreed. It kind of looks like the Hamiltonian, but with more indices, right? It also has to account for all the momenta, okay? And of course in the equation of motion you should have this condition, correct? I'm sorry, the for continuity you should have this condition, agreed? And what is the energy density? Or let me call it some epsilon. That's of course nothing but T00, right? And it's worth writing the expression. By the way, what is the n here? I didn't mention this before. N just labels the fields, okay? I'm just writing this down for a configuration of many kinds of fields, many different fields. So phi 1, phi 2 and so on, okay? It's not some space-time index or anything. It just labels the different fields in the problem. So we've been working with n is equal to 1 basically. Only one kind of field in the problem. Okay, so that's my energy density. Okay, good. Now let's first make sure that for the Klein-Gordon Lagrangian that we had, right? The spin 0 Lagrangian, this is what we had, right? let's make sure as a sanity check that the energy density that we had in this problem was indeed positive definite. Okay. So again, I am not going to walk you through the algebra completely, but all we have to do is take this equation. Okay. Now n is 1, right? So plug this into this and check what happens. Okay. It's trivial to see that the energy density is just dt phi squared plus grad phi squared plus m squared phi squared. So you have a minus Lagrangian and all of that turns into a plus over here as you would expect. And is this positive definite? Of course it is. I am squaring, I'm basically adding 3 different squares here, right? So whatever the field is, the whole thing here is positive definite. So this is a way to check actually whether you got a sign error or something in the Lagrangian. Okay, if you ever wonder should I put a minus or plus for the mass term, for the other potential terms, you can always go and quickly calculate the energy density and check that it's positive definite. Okay, so that's a good sanity check for the Klein-Gordon field, and we are going to apply this sanity check again when we deal with spin-1 fields. Okay, now for spin-1 fields, or spin-1 particles, the challenge, okay, is to embed the correct degrees of freedom into the field. Okay, so let's parse this sentence. What did I mean by this? First of all, let's understand what I meant by degrees of freedom here. All right. Now for a photon, a propagating photon, right? How many degrees of freedom are there? Would you agree that there are 2 degrees of freedom corresponding to the 2 polarizations of a photon, whether you write it as a linear polarization or as a circular polarization? Agreed? Right? So how would I write the polarizations now? In electromagnetism, you would have been used to writing this in terms of 3 vectors, but now we have gone on to relativistic descriptions of all these phenomena, so we have to be more careful, correct? So if you remember, the polarizations were defined as being orthogonal to the propagating direction of momentum, so the momentum basically, right, the propagating direction, correct? And of course if there are multiple polarizations, then I can label that with an I. So I label of different polarizations, right? Now I have to generalize this, correct? So generalize this to 4 vector notation. So that means I can literally define polarizations. Let me just carry the I downstairs so that there is no ambiguity again. I mu equal to 0. So that's the first thing we need to do when we talk about polarizations, right? What else do we need to do? We need to normalize the polarizations. It can't be any vector, correct? And the way we normalize it, these used to be unit vectors when we were dealing with regular electromagnetism, right? But now in the relativistic description, this could be my normalization. Agreed? If I am using the metric 1 minus 1 minus 1 minus 1, then this would make sense, correct? The spatial parts pick up a minus 1, correct? And the temporal part picks up plus 1. So it all works out, right? But this is not all. The polarizations can in general be complex. So this is the convention. I put a star and call this my normalization condition. Okay? Okay, so now with this in hand, can you tell me how I write the polarizations of a photon? And let's say the polarizations are in the xy direction. Let's say that the propagating direction is pz basically. Okay, so let's say that it's some pz z direction, in the z direction, right? That's my momentum. Then how would I write the degrees of freedom or the polarizations? I would say that one of them in the x direction, for the time I am going to set it to 0. In the x direction, that's one polarization. So I am just writing as linear polarizations. In the y, that's another, right? Now these two polarization vectors literally define the 2 degrees of freedom that I have. Literally these are the 2 degrees of freedom, that's it actually, right? Okay, very good. That is for a photon. Okay, this is literally the physical picture of the photon, that's it actually. And this is how I need to somehow embed into my quantum field theory, right? But to make things more interesting, but also to make these things look, to make the flow of logic easier, let's actually consider not a photon but a massive spin-1 field or particle. Okay, so now let me ask, how many degrees of freedom does this have? Surely it can't be 2 this time, right? Something more has to happen if I have a mass for the spin-1 particle, right? So is there any other degree of freedom? You have to think of it from this point of view. Okay, in other words, you have to ask yourself, is there another polarization that we are missing here? Okay, and to answer that, you have to first think about what the 4 momentum is. How do you write the 4 momentum now? Let's still take the z to be the propagation direction. Would you agree that the 4 momentum is now whatever the energy is, 0 0 pz, agreed, such that E square minus pz square is nothing but p mu, which I am writing as p square, right? And of course this is the invariant mass square, that's literally the mass. of this particle, right? Now you can answer using this. Is there any other polarization that you can write down? A polarization vector? Of course, these two satisfy the condition already. Agreed? Then there is one more, of course, that you can write down, and I am going to call that with a label L to stand for longitudinal polarization, and this is the polarization vector that we are missing. Okay, this is called the longitudinal polarization. Notice that if I hit this with a p mu, I do get 0, and also notice that the normalization condition also works out because I have divided this by m, right? So the m square in the numerator and the denominator cancel out. Agreed? So this is literally the third degree of freedom of a spin-1 particle. So when somebody says massive spin-1, you should immediately start thinking of this, because this is indistinguishable from the particle having a mass. This is exactly what it is. Okay, this is not some consequence or anything like that. This is literally the longitudinal degree of freedom along the z direction is literally what we infer as mass for a spin-1 particle. These are exactly the same things. They just look different when we write them down. Okay. Is there any other degree of freedom for a spin-1 particle? No, not really. Whatever else you do, you are never going to satisfy these conditions. We have satisfied the two polarization conditions already. Okay. So there are 3 degrees of freedom. So that's the first thing to remember for a massive spin-1 particle. And the challenge is to embed 3 degrees of freedom into a field theory. You have to write down Lagrangian such that all these 3 are accounted for. Okay. And so we have to begin with a field. Now we can no longer use a scalar field, obviously. So the next thing that is available to us is a vector field, right? It's a 4 vector field. So let me just write this. Embed 3 degrees of freedom into this 4 vector field. Okay. So there is one minimal equation of motion that you can start with. Before you start guessing the Lagrangian, we can begin with an Euler-Lagrange equation that seems to give us the correct answer for how to do this. What is that? It's just the Klein-Gordon equation again. In a different form. Okay. So if you don't like the box is exactly dou square. Okay. That's the notation, right? The box notation. I'm just going to write the Klein-Gordon equation again, except I now hit those terms with not a scalar but a 4 vector. Correct? Now this is a good candidate for an equation of motion, and again from the art of writing down Lagrangians, we can see that you got that equation of motion from a term like this. You can go and convince yourself that if you use this as the equation of motion, you will end up with this kind of a Klein-Gordon equation. Okay, is this Lorentz invariant? It is, because I am contracting covariant and contravariant indices here. I am contracting this covariant index with that contravariant index, and of course I made a little mistake here. This mu has to be a covariant index which I am contracting with a contravariant index. Okay. Now although this satisfies Lorentz invariance and although it seems like you got a nice equation of motion, this won't really do for us. Okay, why is that? Because what this actually describes now is a Klein-Gordon equation for each component of the 4 vector field. Okay, so there is in other words, there are 4 independent propagating modes here. Okay, but we are not talking about 4 independent propagating modes. They are all part of the same particle, right? Correct? All 3 of them have to be connected by the same particle. But here it seems like we are describing 4 completely different particles. We just happen to put them all together into one 4 vector field, right? That's not the only problem here. If you use this, okay, yeah, good. Okay, so if you were to use this as your Lagrangian, then you run into another immediate problem, which is that, let me write that in red probably, because these are problems basically. So this is problem 1, and we have a problem 2, which is that the energy density, if you once again do the math, do the algebra, comes out to be this. You can already see a problem with this, right? That the first term is negative. It's potentially problematic, but you see as I write the second term, things become more clear. So now I'm just picking out the spatial components in the second term, and I have this as my energy density. What does that mean? It means some modes have negative energy, and remember these modes are independent. So even if some modes have negative energy, you cannot say that I'm adding other positive energy contributions, so it's potentially positive definite. No, these are independent modes, so not even a single one should have negative energy, but that's just what we are saying. Correct? So in other words, this is not a good candidate. This Lagrangian is not a good candidate for our Lorentz invariant quantum field theory. Okay, so this is a good place to wrap up for this lecture. In the next lecture, we will see what else can we write down, what other Lorentz invariant term is available to us. Can we write it down and write down a consistent Lagrangian that gives us a correct equation of motion and gives us the correct embedding of degrees of freedom and whether the energy density is positive definite or not. Okay, so we will take this up in the next class. Thank you. See you then.